our lecture.
And this is our last lecture apparently, and week 11, we're going to do some review. Before we do that, I want to show you a book. It's not my book, it's Wolfgang's book. It's called Introduction to Management Science. And so the materials in this book is exactly the same as our module. So just show you the book and you could take a look and pass it around, but remember to return this to me because this is so far the only book I have and Wolfgang have. So please take a look, take some time and pass to your neighbors and later on. And I hope this could be passed around. And after that, you could return that back to me. And this is just to show you we have, every time when I start my presentation is that we got a lot of new audiences. Okay, welcome. And so, and we have this book, and in the book we have actually more exercises and pretty clear answers for every exercise. And you will see a little bit more details about the explanations and details about topics. So that's maybe it's a good reference for your review, or maybe it's a good reference for your future study in management science. Okay, so take some minutes to take a look on that table, on that book. Okay, so if you think that's a really good reference, you could contact Wolfgang, not me, because that's not my book, and contact Wolfgang and in your interest. And I guess he will give you feedback on how to get that book later on. Okay, so we're going to do a review today for final exam. So we briefly review the structure of the final exam and also according to the topics. So what topics are going to be covered and what type of questions will be asked. And of course, we're going to show some of the examples for every single topic. So first of all, this is the structure of everything. Yeah, this is the structure of the, final exam and weekly assignments. I assume most of you 100% finish your weekly assignments so far. And I think the deadline for all the assignments should be December 25th or 6th, or sometimes that should be the end of this semester. You definitely should be finishing everything. Okay, so weekly assignments contribute to 20%. But so far, because actually almost every day I make a phone call and email with the Surrey Learn administration team, and they created, I don't know why, they created a lot of problems and on Surrey Learn. So maybe you will see some problems on your displayed marks on Surrey Learn. Maybe this question displayed, that question displayed again. So that's so, I'm also confused sometimes. So actually, the mark displayed on Surrey Learn might not be the final mark. So as long as you finish all the questions, so all the marks will be calculated based on the questions you answered. So maybe you see very strange marks on Surrey Learn. That's okay, that's fine. As long as you make sure you finish all the questions, that's okay. So maybe, especially for week 5, because I've told them many times we have 2 questions, every question contributes to 2 marks, but they created a lot of problems on that. At the very beginning, they give 1 mark to each of the question, but that's not true. So I told them this should be 4, so they created 4. But previously, you answered 2 questions that contribute only to 2 marks, so that shows 50% on week 5. That's actually not true again. So they created several rounds of problems and of misunderstandings, but that's completely fine. So as long as you finish the questions on week 5, you will get the final marks, definitely. And so you will see from Surrey Learn, so you have questions on week 1, 2, 3, 4, 5, 6, and maybe 8, 9, 10, 11. So this is also one of the problems on Surrey Learn. So you couldn't see your answers for week 7, but actually we do have questions on week 7. So week 7, 8, 9, 10, that displayed as week 8, 9, 10, 11. So I don't know how they're going to create this. So anyway, so if you finish all the questions, so I'll make sure so you definitely get all the marks you deserve. So in total, we have 10 weeks of assignments, but 11 questions in total. Every question contributes to 2 marks. So in total, we have 22 marks. If you finish all the questions, you should get 22 marks. So, but that only contributes to 20%. So that means there are 2 marks are bonus. So the final exam, apparently 80%. So contributing to the final marks, 80%. So if you, for example, and got your mark at 65 in your final exam, but you finish all the assignments, so you receive 22. So in total, you will receive 74. So that's your total marks. That's actually okay. So it's a distinction marks. So this is about weekly assignments, and I hope you could finish them very easily. And for the final exam, so that should be around January 14th, I guess, because I guess you received the email of the arrangement for all the final exams. So that contributes to 80%. So we're going to have a closed book, paper-based final exam. You don't have to using Excel, but you should using your calculator to calculate something, but no Excel, no optimization. So you don't need any software to solve the problems for you. So everything should be solved by your hand. So paper-based, and you will have 4 questions covering 4 topics, starting from very simple linear programming, transportations, and waiting line system and inventory system. So every topic contributing to 25%. Yeah, please. So, sorry? So probability is a preparation for waiting line and inventory system. So when we have that lecture, so that's actually a sort of a review. So we don't have a question asking you to normal distribution or whatever probability calculations. That's actually a review of, because review that is preparing topic for waiting line system, because that's basically based on the probability. So we say everything is on average, and so you should calculate your expected values. That's actually when we're calculating the numbers of the customer in the system, that's based on probability. So that's a warming up things, because that's not one of the major topic for this. Okay, 4 topics. So we are going to have 4 questions of 4 topics on your final exams, and every question contributing to 25%, and you only have 4 questions. You have to answer them all, so you don't have any choices. So, okay, so this is the basic structure of the final exam. So we are going to review the 4 topics one by one, but it's not possible to covering every single corner of the whole knowledge systems in this module, because we've done that in the previous 10 weeks. So we're gonna just pointing out some key points, some major knowledge, some major outlines of this every single topic. Okay, and first one, linear programming. So we started from, you have a question? Is that, I saw you raise your hand. Okay, so. Okay, please come in. And so we have, we started with the linear programming in first and second week. So linear programming is actually trying to solve pretty straightforward problems. Usually, we are trying to analyze a very simple business story. And in a business story, we should have a target. So we call that objective. We're trying to minimize something or maximize something. So, and you have to identify the objective. But sometimes that's actually part of the question. So very easily to identify what is your objective. And you have to know what is your decision variables. And maybe you will see a lot of things, objects, and products in the questions, but you have to find out what are crucial decision variables, maybe one or maybe two. And also, you have to find out the constraints. Is there any limits? So how much time you have, how much money you have, so how many raw materials you have. So basically, this is something you have to identify from a question, from a business story. So, and the question format is actually, I guess you saw this before. So this is a very typical question. So you'll be given a story. So usually that's maybe longer than this, right? They're gonna tell you one day you're a businessman, you are running whatever shop and bakery shop, or this is one of the typical examples, and you have to bake this and that maybe, but your time is limited, but your raw material is also limited, but now you hope you can maximize your profit or minimize your cost, something like that. So this is one of the typical example of the question. So in here, it's you are Jane or Jenny. So you are running a shop. You hope to bake something, but apparently you forget something, and you promise your friends you're gonna make some cakes or some breads. So you have very short time to do all the tasks. So you have 3 hours available, and you have to make some cakes or some bread, some loaf. And so we know the materials you need for basically a cup of cake and also a loaf. So, and also you know the price on the market, and now you know how many raw materials you will need. So this is loads of different conditions and informations. And now you have basically have to identify several things. So this is usually the format of the questions, starting from very fundamental, very simple things. Summarize the information in a table. That's actually a very good step for your future calculations. So so far everything is pretty messy, so you have to summarize everything into a table. So the tables are very similar to the table in the lab sessions. We actually have summarize everything in Excel table, but now we don't have Excel. We should have a quite small table and identify everything. So what products you have to make, so what is your requirements, so what is limitations, time, raw materials, and so is there any price or market price and any profit you can make by doing those products. So, and also you need to draw some lines, because this is a straightforward linear programming problems. So usually we have 1 or 2 variables. That means we can easily to draw some lines and to represent the certain conditions. And we could find out what is the feasible regions for our answer. And also we can probably find out all possible solutions, because for this is to make some cake and bread. So that means everything should be integer. We should make 1 cake or 2 cakes. It's not possible for 1.5 cakes. That doesn't make any sense. So let's take a look at how we're gonna solve this one by one. Okay, so the first one. So this is usually the table you should summarize on the paper. So we have to make 2 things, cake and bread. So apparently, and we know the raw materials we have to consume for make every unit of cake and bread in here. So, and we know the time. So pay slightly more attention on the unit of the time. So we have only 3 hours. So in here this is hour, and the cake requires 45 minutes. So you have to convert between hours and minutes. And revenue, so this is actually the market price you can make. So this is all the essential information. So that's pretty easy. You have to identify everything and from the story and list them in a table. So this is pretty easy for yourself to do the future work. So the first question, I think it's pretty easy to have 5 marks. And the second one, draw a graph. So this might take slightly more time and because usually the graph represents the constraint. Because this is the table we have in the last question. And we know the limit, 20, and so 3 hours. So apparently we don't know how many cakes, how many breads we should make to maximize our profit at the same time maintaining or satisfying our constraints. But we know this is definitely our constraints. We don't know how many cakes and bread, so we give some variables and cake and bread. So this is the time limitation, and also this is the raw material limitations. So we know if C represents how many cakes and B represents how many breads. So apparently we should have this relationships. So if we have the relationships in here as the two equations in here, so we should represent them in, as a graph. So in your final exam, you will have this graph paper with this grids in here. So you could very easily to draw the lines on this graph paper. And you should be very careful about the points. You cannot just show, okay, I just draw a line, but you don't know the points. So you have to calculate the points in here. For example, for this. So this is for the raw materials. So the equation in here is a 3C plus 8B smaller or equal to 20. So how to draw this line? So we discussed this before in the lecture. So the easy way is we make this to be equal. And then we try to find out 2 points, because 2 points determines a line. So what if C equals to 0, or what if B equal to 0? So that's very easily to calculate the other one. If C is 0, so B, that should be equals to 20 divided by 8. That's pretty easy to find out what is B. So you should clearly know where the B is. So what is the points? Otherwise, it's really not possible to figure out. So this is 2 or 3 or whatever. So you should very clearly know, so what is the point in here. And also, because this is pretty small, so maybe you have another point in here, so you should also know what it is the number of this. So to calculate this, apparently we should make B to be 0. If B to be 0, C is 20 divided by 3, so that's pretty easy to find out. It should be 6.6777 or whatever. So find out that point, and you should have one line. And so after the first line, you could, by the same way, calculating the other line, so like this. And then you will have basically intersections somewhere, for example, like this. And okay, so, and then you will have regional feasible region as this, because we know, and we should, the values of this equation should be smaller or equal to 180, and this should be smaller or equal to 20. So smaller, that means below. So you could very easily to verify this by using some easy points like a 1, 1. So if you substituting 1, 1 into here, so that apparently this is smaller than 180. So that's a feasible region. And so I guess maybe in your final exam, this takes some time to finish, because you have to identify the points and draw a clear graph. I'm not saying beautiful, but make everything very clear. So, and write down very clearly, so what is the point at here and what is the point at here. So you have to identify the points. And okay, the next one. So identify all possible solutions as solution value to these problems. So once you have 2 lines, you will have this feasible regions. So you could try to solve, because this is pretty easy to solve. If you could solve that, that's fine. But actually, you could have a lot of combinations of C and B, of how many cakes and breads you could make to satisfying the constraint. So they might not be the best or optimal solutions, but they all satisfying the constraints. So that means as long as the B smaller than this point, and C smaller than this point, and as long as they are in this small region, so they should be all feasible. So they satisfying our 2 constraints. So you could, because for this question, it's pretty easy to find out. We could possibly having C equals to 1 or 2 or 3. So maybe for 4, so 4 should be the point at here. And for B, that should be 0 or 1 or 2. So we should have a small table of this and listing all possible values of B and C. And because we know how to calculate the total profit, because we know the profit and we know the price for the cake and bread. So we substituting every point into this and to find out the total profit. And apparently you can find out which one is the highest one. So it's 4, 0. So that this is the highest one. And show them on the graph. So it's apparently we could show all those points on this graphs in here. And so in a table, I select the best one. Apparently this is the best one. So 40. So that's the highest profit we can have if we satisfying all the constraints. Okay. So this might take slightly more time because you have to identify how many possible combinations of variables for B and C for 2 products. Okay. Excuse me. And this is question number 3. If you could solve this, apparently for the last 2 questions, that's pretty easy for you. So we actually have done this in previous questions. So this is the constraint and this is the objective functions. But try to remember this. Because sometimes it's very easy to forget this. And so apparently we should have a positive numbers of cake and positive numbers of bread. So we are not going to make any negative numbers of cake and bread. So this should be higher and smaller and then higher or equal to 0. And you could also write down, so C and B should be integers, should be a whole number. So we don't make 1.2 cakes. That doesn't make any sense. But if you don't write down as an integer, that's also okay. But they should definitely higher or equal to 0. So this is the compulsories. Okay, so I guess this is not very hard to solve, but might take some time if you need to calculating for all the combinations in here. If the combination takes more than this, if you have to calculate from 0 to 10, but usually we don't make that type of messy calculations. Okay, so this is usually the format for linear programming. And yes, please.
For the objective function, when you calculate it, normally the maximum benefit or profit you can reach is the one you calculate. Yeah, the one that is like.
The one maybe at a corner, maybe here or this.
Yeah, but most of the time is the one at when x is when y is 0. Okay, but in the exercise that we have,
yeah.
When you see the answers, he or she, like the person who has done it, always says that the profit, the maximum profit, is the one that
Of this one?
Yeah.
Ah,
and
okay.
sometimes it has more revenue.
Okay, so actually we discussed this in the lectures. So how to identify, because if we have the feasible regions, so this is apparently the boundary. So maybe the optimal solutions could be here or maybe here. So how to identify? Because we actually have one method, because the total profit function is this, because this is something we hope to find out. And so if you take a look on the slides of lecture number 2 or 3, maybe number 2. So we actually need to draw a line, straight line of the profit. So this is actually the profit line. So maybe the profit line starting from here, because we don't know what is the whole profit. So we give it a random number, for example, 1 or 0 in here. And we can draw the line, because this is also a line of C and B, 2 variables. And apparently this is the feasible region. We don't know where is the optimal solution. So we're going to moving from this in here, for example, and moving from here to this direction. Because we know, so this is a feasible, and outside is not feasible, because outside is basically break our constraint. So we're moving this out, so the last touching point of the profit line and the feasible region will be the optimal solution. So think about if you have a line at like, for example, for example, if you have a line something like this, pretty bad drawing. So moving from this direction, so probably the last points will be here or here. So apparently the last point, there should be sometimes in here, because this is a pretty sharp. But what if you have a line like this? So apparently the last touching point will be here, because this is a pretty flat. So if you moving to this direction. So how to determine, so this is a sharp or flat. So this is actually determined by the price. So 10 plus 6b, because you could, for example, you could give it for example, what if I want to give a total profit of 5? This is apparently not the optimal one, but we can have an equation, 5 equals to 10c plus 6b. You could draw this line. And so once you draw this line, so basically the lines is determined by, so the sharp or flat is determined by 10 and 6. So this is actually your price. So if you change your price, so your profit line, so maybe from flat to straight, so that's whatever shapes might be have. So once you have the fixed price, you will definitely have a fixed format or fixed shape of your profit line. So maybe pretty flat like this, or maybe straight. So that is actually fixed. So, and when you have your fixed line, so you're moving, so apparently your final touching point is also fixed. So that's also determined by your total profit lines.
Okay, so we could say that maybe the answers are wrong. If cooking for bread and no cakes gives more revenue, cooking 4 and 1, I have to choose the 140, or it is not the one that I calculated, right?
That should be the same. So if you looking at the graph, or if you calculating for all the possible solutions, that should be the same. It's not two different things. I think okay. So if we have more questions on this, I wanna slightly going back to. I guess should be, oh, no, not here, not this one. Yeah. Okay, so this is actually what I was talking about. And okay, so yeah, this is the example, and we've done in the first or second lectures. Oh, that's a lot. So, and we hope to make sure. So where's the starting point of this? Okay, anyway, we could possibly starting from here. So if we have a one constraint, so that's easy to draw a line of one constraint like this. If the constraint is like, yeah, if this is our first constraint, so apparently, so we could assuming, so this is one of the problems, so we should determine how many wild basmati or pure basmati rice. So two different products. So this is a one constraints, so about the time, and we have another constraints about the raw materials. So apparently, so we don't know, so which point, so it should be this point or this point, we don't know. So pretty similar to the question. So, but we know, so this is actually, the feasible region is the A. So A is the feasible region, and so B, C, and D are all breaking some or total all the constraints. And Okay, 40 and 50, they are actually the prices for the two products. So we don't know. So because we could make the profit to be 2,000. That's just one of the examples. We could make it to be 2,000 by making certain x1 or x2. Okay, so if we have this, so we can apparently draw a line of our profit. So apparently, so this profit line is something like this. So this is a pretty flat. So, and 2,000 is pretty big. If we're moving from here to this, apparently we are going to breaking the constraint more and more. So this is not the right direction. So we should moving slightly down from here to here. So this is actually how we're gonna moving this. So, and we could apparently achieving here in a corner. Okay, because this is actually the final point we are going to reach. So if we're gonna take a look on this again. So if we're moving this to this small area, because this is the feasible area, and we don't know, maybe the optimal points should be here, or here, or here, all possible. So we moving the line. So apparently this is the first touching point. So if you're moving from downside to up, the last touching point should be also at here. So this is definitely our
in this case, it will give
yes.
you not a fixed number, like not a natural number, because it's, for example, I don't know if it's.
You mean fixed number of what?
Can you go back, because there was like a line? No, after it appeared like a line to show the profit, like a square, red square.
Red square.
No, like next. Yeah, next. And next. And next. Okay, now.
So this is not a square actually.
Yeah, I know. But I mean, does this give you like 24 exactly or 23 point something?
So I hope I understand your question. So you're asking, so what if we know, so this is the touching point, how can we identify the number? So how many pure or wild rices we need to produce? So is that your question?
The question is, what happens if your answer...
I've answered that. So what happens when the theoretical value, the mathematical solution,
Mhm.
is not the same as the solution, the real solution? Because it's, for example, you're producing a box of something and you have to have a certain number, a whole number. What if that's not the mathematically correct solution? Is that the question you're trying to ask?
So but actually, you should have. This is actually, if you think about this as mathematical things, so this is always be the optimal point. But actually, we have some other, like for example, we should have make this as basically a whole number. So apparently, this is not a whole number. So this is a theoretical solution. But if we hope to make this as a whole number, so this is apparently this is not the final results. But if you think about a whole number here, so we have to moving this slightly more down here because we have to satisfying the whole number and constraints. This is another one. So, but this is not something different. So because if we only calculating the math, that could be whatever numbers we can achieve, 23.6 or something, but that really doesn't make any sense if we make a whole product, because this is a bag of something, and so this is not a problem at all. So if you hope to show, so this is optimal points, so this is always be, and from the figure, so this is always be the optimal point, but that might not be giving us an integer solutions finally. So, but that should be fine. So this is not the different things, but this is just how many constraints you have to meet. If we only consider math, that's okay. But if we have to consider, but of course, integer is part of math. If we consider the integers, so this is something we have to consider more. Okay, okay, no problem. Okay, So, yeah, the last one. And after the first part, the first topic, and the next one, transportation. And in the transportation, we discussed 3 problems: minimal spanning tree and shortest path and maximal flow. And minimal spanning tree is only about the connection. So if we have a number of stations, train stations, for example, so how can we connect them all by the minimal and total distance? And shortest path, apparently we should, starting from a source to a destination, find out, minimize the total distance we traveled. Maximal flow, this is slightly different from the previous 2. So maximal flow is if given a fixed network of the traffic, so how can we utilizing this traffic and network to transport as many as possible for ourselves? So this is 3 questions. So the first 2 is minimizing something, and then last one is maximizing something. Okay, so we try to do some questions, and so usually this is one typical and format of this type of question. So we're given a certain network, and we give you a small and business story. For this is about transporting from Manchester to Edinburgh, so through this network. So this is a fixed, but you have loads of different numbers in here, so please read carefully about the meaning of those numbers. In here, so we have showed the network flow capacities. For instance, the maximum flow capacity from node 1 to 2 is 10 wagon per week, and the opposite direction from 2 to 1 is 4. So if you're looking at here, so this is a 10 and 4. So 10 means 1 to 2, so the maximal capacity, and 4 means 2 to 1, so another direction. So if you're looking at this, 2 to 7, so we have 7 as a capacity, but 7 to 2 is 0. That means we cannot transport from 7 to 2. So this is the meaning of those numbers, so the meaning of those capacities. So apparently we can transport 1 to 2 to 7, or 1 to 3 to 5 to 7. Also, maybe 1 to 3 to 5, maybe to 4 to 6 to 7. This is all possible. So now what we hope to do is what is maximal number of wagons that can be transported from Manchester to Edinburgh through the fixed and network of the rail. Okay, so this is the maximal flow problem. How can we find out so the maximal output from here, 7, and starting from Manchester? So, and usually we have several questions like this. So we need to formulate a generic structure solution, and we give some descriptions of how we're going to do this. And then, so we're going to calculate for every single path, so how many and capacities we need to use, and finally we should reaching a maximal number. So let's take a look on this. So the first one, how are we going to find out the maximal flow? So this is actually pretty similar to the descriptions in our lecture. So you don't have to write down exactly the same words as the solution, but you should give very similar descriptions on this. So to find out this, so we should basically arbitrarily find any of the path from the source to destinations and identify the capacity, because for every path we have different capacities. And once we identify the capacity, we should do some subtracting the maximal flow from the capacities and find out so how many capacities left. And then so we could add the maximal to the output, and we're going to repeat this. So every time we find out so how many capacity left, is there any other options we can transport more and more? And every time when we find out a path, we subtract, so this is the maximal capacity to the actually transported capacities. Okay, let's try to do this. And apparently, if we hope to find out the maximal one of this figure, and we should first step, arbitrarily select one of the path, we can very easily usually from 1 to 2 to 7. So that's pretty simple. If we transport from 1 to 2, it's possible to transport 10. But from 2 to 7, apparently the maximal is 7. So we have to identify so how many from 1 to 2 to 7. So the maximal should be only 7 because we can only transport 7 from 2 to 7. So this is actually what we can do. So this is the first path. So we know, so 7 is the number we can transport from 1 to 7. And after we identify the 7, we should do some subtraction. So in here, the capacity, the maximum capacity is 7. So apparently we use them all. So that 7 minus 7 is 0. So far, we cannot transport any more from 2 to 7. But we still got some capacity left from 1 to 2. So that means maybe we can transport for some others from 1 to 2 and maybe to 3 or 5 or 7, maybe. We don't know. So, but so far, we have 3 left from 1 to 2, but 0 from 2 to 7. So that means, okay, so this path, basically, so we couldn't use this path anymore, so because the capacity is 0. Okay, so this is the first path. And then we're trying to figure out another one. This is pretty easy, 1, 3, 5, 7. That's also possible. So 1 to 3 is 15, so the maximum capacity, but this is 12, this is 10, so this is pretty easy to identify. So the maximal and we can transport from 1 to 7 is just a 10. So, and after that, we can substituting 10 from here and here and here. So apparently, we use all the capacities from 5 to 7. So there's 0 capacities on this path. But we still got 2 left and 5 left. And the next one, the final, is not final. So here, the capacity is 5, and here is 5. And here is also 5, because this is the maximal we can afford. So once we have done this, so we subtract 14 and 5, so this is a 0, and again, so this is a 0. No, this is a 13. We still got 13 left from 1 to 4, but from 4 to 6, so the capacity is 0. Okay, so, and if you're looking at this, so basically, we still have some capacities left, but it looks like we couldn't make any transportations, because if we hope to transport to 7, so here's one of the choice, and this is 0 so far, and this is also 0. We got some capacities from here, so it's actually maybe we can do something and from this to here, but apparently if we hope to transport something to 6, so 4 is the point we have to pass by, but apparently, so from 4 to 6 is 0. So that means basically we couldn't do any more transportations, sadly. So, and that's actually everything. So we couldn't do any more transportation. So the maximum is 7 from 2, 10 from 5, and 5 from 6. So in total, it's 22. That's the maximal number of the traffic we can transport from Manchester to Edinburgh. So this is actually pretty easy. And there's several ways to, yes, please.
How do we know that the capacity is 7, 10, and 5? Like from where we get that?
Sorry, 7, 7, 5?
7, 10, and 5.
7, 10, and 5?
Yeah.
How do we know? Because this is, we actually using a whole process to identify, so this is a 7 or 10 or 5, because this is the process. So at the very beginning, we don't know. So we randomly or arbitrarily select whatever path and figure out, so okay, so the first one, the maximal capacity we can transport is just a 7. So we figure out this is 7. And then 10, then 5. So this is the process of working this out. So, and finally we know, so this is a 7, 10, 5. This is everything we can do to maximize our flow. Yeah, please.
What if, for example, we tried to go from 1 to 7, but what if we...
Yeah.
Yeah, what if we went from 1 to 4, then from 4 to 5, and then from 5 to 7?
5 to 7?
Makes sense to...
5 to 7. You mean based from now or from very beginning? Yeah, it's all possible. I'm not saying this is the only result we can achieve, but as long as your solution makes sense, your solution has your logic, because there are loads of different options in here. So you can arbitrarily choose whatever. You can choose 1 to 2 to 3 to 5 to 7. That's a pretty complicated path, but that's all okay. So, but try to make your solution as simple as possible. You will make a lot of things messy together. It's really not easy to identify the final ones. So this is a simple case, because this is a pretty straightforward from 1 to 2 to 7. Okay, it's the first one, and we've done this. And then 1 to 3 to 5 to 7. That's all okay. If you want to start it from 1, 3, 2, 5, 7, for example, that's all. But that's pretty messy things. Yeah, that's all okay. This is not I'm not saying this is the golden or the only solutions. You can try different things, but maybe the maximal output is the same, but basically, the process, you're working this out is slightly different. That's all fine. And you don't have to show every single step, but you have to show finally, how many traffic, how many capacities you could use at every link, every path in here. So you could have a small table, say 1 to 2 is a 7, or 2 to 7 is 7, or you can just write it down very clearly on the figure, so on this graph, and write it down. This is a 7 and 10 or 5. So these are all your solutions, whatever you want to do. So, but finally, you show how you achieve 22. So because you have a 7, 10, and 5 from different nodes going to the output points, and you have your final output as 22. This is one example. Any more questions on this? Okay, so, and another one, minimal spanning tree. So I guess this is slightly more simple than the previous one. Minimal spanning tree is only for connections. So we have 1, 2, 3, 4, 5, 7, 8, no, 7, just 7 nodes. And we have the connections between some of the nodes. And now we hope to find out how can we connect them all by making, and at the same time minimizing the whole total distance. So this is usually the typical questions. So the first one is pretty simple. What are the components of the network and what the edge is at least the distance? This is a pretty descriptive questions. And then determine spanning tree and total required length. And so formulate the solution. Just briefly describe how you're going to do this. So this is actually description of the algorithm. So let's try to do this one by one. So what is components of this network? So apparently we have nodes, edge, and weights. That's pretty straightforward. We have 7 nodes, and we have edge, 1, 2, 2, 5, 2, 4, and 3, 4, something. And for every edge, we have a weight. So in here, so the weight means the miles, so the distance. Sometimes maybe the cost or something. That's based on the different stories of the question. So in here, so this is the weights. And so, because this is a graph. For a graph, so basic elements is the node, edge. So edge connecting the nodes, and also the meaning of the edge. So that's actually the weight. So in here, weight, we have several different weight. And so which edge has the least distance? So apparently this is 4 to 7. So this is just 9. It's pretty short. And so give an example of a cycle that we like to avoid. So we have loads of different cycles in here, just to give whatever example. So 1, 4, 3, so this is a cycle. We don't like to have any cycles when we trying to connecting the whole tree, minimal spanning tree. Okay, so, and this is straightforward question. And then we hope to work out and this minimal spanning tree. Usually we're going to find out a starting point, not necessarily to be 1, but usually we like to starting from 1, so as a tradition. So if we're starting from 1, so we hope to find out the shortest distance connecting to 1. So there are only 3 options, 21, 30, and 17. So that's apparently 1, 2, 3. So this is the first path. When we have 2 points, 2 nodes, 1 and 3, now the next one we hope to find out is the shortest path connecting to either 1 or 3. So we have more options, 21, 30, 12, 25. So apparently we select this. This is the smallest. And then we have 1, 3, 4, 3 nodes. And we have a lot of others connecting to either of the 3 nodes. So we find out the smallest and shortest. So apparently this is the shortest. And then basically we have to consider all the others, because all the other nodes are connected to either of the 4 nodes so far. And we find out there are 10, another 10. So apparently we should connecting them. And then, so we should still have 1 remained outside. So we're going to find out 12. That's basically the shortest connecting to 7. So that's going to be our final minimal spanning tree. So how many miles we have to travel for the whole tree? So apparently we add them all. So this is the total miles. And what is the total required miles and in general relationship number of nodes and number of edges? So we have 7 nodes, but 6 edges. 1, 2, 3, 4, 5, 6. Yeah, it's 6. And try to formulate solutions in words.
Is that everything you have to write for that question? Like
You mean this?
how many? No. When they ask you in general what is the relationship between the number of nodes and number of edges?
So that's actually you don't have to describe more about the relationships. It's just to show how many rows, how many nodes, and how many edges. Yeah, that should be fine. And about the solution, so this is pretty descriptive things. And randomly selecting the starting point, and if you only have 1 point, so find out the closest, and select the closest node not currently in the spanning tree. So, and it won't form any cycle. So, and repeat this until we include all the nodes into the tree. Okay, so this is pretty standard things, and you don't have to write exactly the same, but express the very similar meanings and similar and process how to work out this. Okay, so this is any more questions on the network? Okay, and next topic, waiting line. So in waiting line system, we covered basically 2 major types of waiting line system, and it's a single server system and multi-server system. So for the single server systems, actually, I think we have solved this many times. So this is a summary of the single server systems. So we have basically several things. Number of customers, and the time, and also the rate. So the service rate, arriving rate, so that determines everything. So 3 crucial things. And so let's briefly go through this. So the probability of 0 customer in the whole system, that's purely determined by the role, the utilization. And the utilization is defined only by the 2 rates. We only have 2 rates, service rate and the arriving rate. So arriving rate divided by the service rate, that's our utilization. And we have 2 mathematicians. So the first one identify the number of customer in the whole system by the probability. And so we try to calculate the probability of 0 or 1 or 2, and finally we can calculate the total number of customer in the whole system, and we reach the final end result. So this is also determined by the utilizations. But another mathematicians identify the relationship between the number of customers and the time the customer are going to stay in the whole system, and the lambda, the arriving rate. So but before we working out those equations, there is one assumption, is that we only consider 2 components of the whole system. So that means the queue and service, waiting and service. So we don't consider any other things. So if a customer going to a shop and immediately waiting in a line to be served, and then so he is served, and then after the service, so he left. So this is the only two components. So so the relationship holds for the two components, waiting and the service, respectively. So we have the same equations for the waiting in a queue and a service. And for the service, apparently we could have the service rate. So this is something we should identify. Usually we know the service rate for most of the cases. If we know the service rate, apparently we can calculate the time, in average time of a service for one customer. And then we can substituting, we can identify the basically ALS, that's the number of customers in a service. That's basically determined by the utilizations. So this is for the service. And for the queue, so apparently if we know the WS or the whole W, we can calculating the time in a queue because we only consider two components. And so we can using the total time minus the service time, that's apparently the waiting time. And also this is the very traditional equations. So the number of customers in a queue also equals to the arriving rate times the time in the queue, average time in the queue. And also we can, from another point of view, so the number of customer in the queue waiting there equals to the total customer minus the customer in the service. So, but the customer in the service is only determined by the utilization. So we could finally work out these equations. But this is all for the single service. And when we come to the multi-service, so all the formulas will became much more complicated. But you don't have to remember all of this. This is pretty messy. And you'll be given, but you should understand the meanings of every lambda and mu arriving rate. And so what is C? That's actually the number of servers. And okay, so I want to use an example to show how we're going to calculating this. And people going to bank. So this is a very traditional case of waiting line. If you go to bank, you take a number and wait in the queue, waiting to be called to one of the counter. So apparently, usually in a bank, we have a multi-counters. So and in this, we have 3 counters. So and a single counter can serve 10 customers. And so the arriving rate is 25 per hours. And also we hope to make sure the waiting is no longer than 6 minutes. So this is all the information in here. And we have pretty traditional and questions. So what is arriving rate, service rate, inter-arrival time, service time? That's normal questions. And what is the utilization of 3 counters in this system stable? And also we need to calculating the average number of customers in the system and also in the waiting line, in the queue waiting, and also in. So this is basically the traditional things. And those are the formulas, given formulas. So P0, what is P0? Yeah, probability of no customers. So why do we need this? Because we need to P0 to calculating queue. So this is the average number of customers in the queue waiting there. So and we need to P0s. Okay, if we know all these equations, so probably we can calculate them all. Arrival rate, so we know the arrival rate, 25, customer per hour. So we have to write down the units. So I want to emphasize this many times. So every year, we have some students calculating everything correctly, but without even a single unit. That's actually very sad. So you couldn't get your full mark. If you're calculating everything correctly, but you don't write down even one single unit, that's so sad. So you might have a lot of marks deduct. So the units is very important. 25, you have to say 25 what? 25 customer per hour. It's not per minute. So it's write down the unit. And service rate, 10 customer per hour. So this is based on the time and based on the customers. Okay, inter-arrival time. So apparently we should using either 1 divided by 25 or I like to using minutes, so this is also okay. So 6 minutes per hour and 25 customer per hour, so we can calculating 22.4 minutes. So you don't have to use in minute, you can use in hours, or whatever unit you like to use. That's all fine, but you have to write it down. So this is a hour or minutes, you have to write it down very clearly. Also service rate, so we can using 6 minutes or 1 hour, that's all okay. So you can see you can using 1 divided by 10 is 0.1, but that's hour per customer. So I'm using minutes, so this is a 6 minute per customer. Also utilization, so because we consider the utilization of the 3 counters, so you should times C equals to 3, and time 10 times 3, and divided by 25. So we got this utilization. So this is a percentage. Okay, and second question, how many customers are on average in a waiting line system? How many are in a queue and how many are being served? So customer, how many customers? So if you think, wow, it's really not easy to calculate, but if you going back to the questions, so this is all the equations you will have, but you have to identify which equation, which formula you could use. So apparently we have P0, so this is something you can directly calculating from the informations. And also if you have a P0, you can calculating LQ. What is LQ? That's the number of customers on average in a queue. So apparently Q is starting from here. So starting from calculating the P0, and take a look on this equation. It's pretty long, so you need C is the number of server, and lambda, arriving rate and service rate. And so this is also C and C mu, so you substituting everything, but make sure your calculation is correct, and you have to find out, so this is -1, that means 1 divided by a lot of these results. And then you got a probability. So this is a 0.04. So because a P0 is a starting point, so I like to keep pretty long decimal digit to make sure the following calculations are basically the more accurate as calculated as possible. So this is what I like to do. You can also keep this pretty small, for example, 0.04, but that might give you some of the tiny errors. There's not error, so tiny difference between the standard answer and your answer. That's all fine, but my suggestion is that as the starting point, when you're calculating P0, and you should keep as small as the decimal digit as you could, for example, 6. And I think that's very okay for the starting point, because you have to substituting P0 to the following calculations. So if you keep this pretty small 0.04, that might give you some truncation errors in the following calculation. Okay, so when you have P0, apparently you could calculating the further by using this equation. So this is pretty long, so you could be very careful about and every single variables, lambda and mu. And I guess one thing is pay more attention about the unit. So the lambda is 25 per hour, so the 10 is also 10 per hour. So maybe sometimes in a question, they're gonna tell you the lambda is based on the hours, but the service rate is based on a minute. So be careful about that. So you have to convert the numbers by yourself. Okay, so if you're substituting everything, you could easily use your calculator to find out their solutions. So this is on average 3.5112 customers on average in a queue. And once you have this, so apparently you can keep calculating for some others. And this equation is also given, you should calculating the total customer in the whole system. When you have a total customer, and you can easily to have your customer number in the service. Okay, and if you calculated everything, and apparently you could find out the time in the queue and the total time. So that's apparently pretty straightforward following the equations. Okay, so waiting line, any questions for this example? No? Okay, so the last part, inventory system. So we have discussed EOQ and EOQ non-instantaneous receipt and EOQ with a shortage. So, and I believe you've seen this before many times. And to identify which an equation or which model we should use in production, that's one crucial thing. If you see some production numbers in your questions, so most of the cases you have to consider for non-instantaneous receipt because you have to consider your production. Yeah, please.
Will we get him these formulas?
So I'll talk that later. So, and I guess maybe the crucial thing is identify and which model you're going to use and identify the certain variables. And so what is P, what is a capital P, a small p, and Y, and calculating those costs. And I want to show you and answer the questions about the formulas by using one of the examples. So this is pretty standard and typical examples of this type of a questions. So if you're looking at a question, so this story is pretty simple. And you produce something, and you're working for some days, and then you shut down your production line, and waiting for some days, and then you start the production line again. So this is usually the format of the story. And you should calculating optimal production run, so Q, that's the crucial things. And once you have your Q, you should calculate the total annual inventory cost, and also optimal numbers of productions and cycle time and run length. And for this, and this is the only questions you will be given. So actually this is a very good hint because this is the only questions you will be given. So apparently you're definitely using this models. So that basically tells you which model you have to use. So apparently for this is this model. You know the productions. So what is our production? So produce coconut chocolate with a rate of 1,000 package per day. So this is a daily production. So you know this is a daily production, and also you know the demand. And so what is the demand? We know the annual demand, and also we know how many days we're gonna working. So we could know what is small p, small d, and everything in here, and also the equations. But this is the only equations we have. So we could easily to identify the days. So 365 days a year. And so this is a production, daily production. And so this setup cost, the holding cost, and this is all the conditions we know. And we know this is a demand, annual demand is pretty big demand. We can calculating the daily demand based on the annual demand and how many days we're gonna working. So, and we know everything, so we can easily to calculate this. That's the optimal Q, optimal quantity of orders for every times we run this production. And once we have this, so we also know the holding cost formulas and setup cost formulas. We can calculate them respectively. Or if you make sure one of the calculations is correct, you can apparently calculating just either of them and times 2, because apparently they should be the same. So if you're calculating them separately, they are the same. And you add them all, so that's your total inventory, total annual inventory cost. And once you have those, you have a Q and you have the cost, and now you should calculating the optimal number of production runs and also the cycle time. But for those 3 questions, the equations will not be given. You have to understand the meanings of that. So optimal number of production runs. So we know the total demand and we know the Q. So that's actually, so how many times we can easily calculating. So 20 times. And if you need 20 times, so and you're working 365 days a year, so for every time you have in average 17.83 days. That's for one cycle. And optimal cycle time, so you can also answer that in weeks. That's also okay. So usually 25 weeks, that's the weeks in a year. But if you're given 365, a very easy way to calculating how many days. But if you answer weeks, that's also fine. So production run, so that's actually based on the Q and your daily daily productions. So daily production is 1,000 package per day. So, and one queue is more than 4,000, so it's pretty easy to find out how many days you can make, you can run the production line. Okay. Any questions so far for this? Yes, please.
Some of the numbers, like the days, would you then round up to 5 or would you just leave it at 4?
You mean this? I think you could just write it down like with some decimal digit, because this is the average things. So we are not saying this is exactly this day, but this is on average how many days. So it's perfectly fine if you have 4.87 days. That's okay, because it is average. Yeah. Okay, so that's almost everything we should cover for the review. And exam should be this date, and January the 14th, and 2 hours paper-based exam. Okay, and so, and the last thing is I'm going to leave, and today is your last lecture, and also my last working day. So I'm going to leave to University of Edinburgh, so from January of 2019, but I'll still be responsible for this module. So but I'll not be on campus or office after today, but I'm still replying your emails. If you have any questions, send me email. But if you really want to see somebody, maybe you're going to have to go to Wolfgang's office to see him. But if you have any questions, you can send me email. So I think my email address should be valid until the end of February. So I should be able to provide whatever help you need for the final exam. And also, I'll be marking your final papers. So all of the reviews should be fine with the final exams. Okay, so thank you, guys. Thank you for the whole semester. Thanks.